In this video, we're going to solve a problem that utilizes Newton's third law in one dimension. The first step is to visualize what's happening. I have a tension that's pulling this mass A of 40 kilograms across the ground. It's accelerating at a rate of 5 meters per second squared. The surface between it and the ground is frictionless, but there's another mass, B, that sits on top of mass A, and it slides to the back as mass A accelerates forward. But it is still accelerating to the right at an acceleration of 4 meters per second squared. We want to know the magnitudes of the frictional contact forces between the blocks and the tension in the string. I'm going to use Newton's second and third law. I'm going to start with Newton's second law. I'm going to choose an object and then look at the forces on it. So I'm going to start with mass B because that just looks the simplest to me. What are the forces that act on mass B? Well, the first thing I can notice is that I'm going to stay in one dimension. I have my sliding object model where mass B can only slide in one dimension as long as it stays on mass A, and it does. So as long as it stays in one dimension, I'm ignoring the forces in the vertical dimension and treating this as a one-dimensional problem. So what are the forces? There's really just the one. A contact force has to cross this line, and so there's a horizontal contact force, a frictional force, that has to be in the same direction as the acceleration, so we know that that frictional force is to the right, because we're told that it's accelerating to the right at 4 meters per second squared. Well, if that's the only force, it's pretty easy then to come up with a scalar expression. In my one-dimensional model, I just have the magnitude of the force where the sign indicates the direction. In my free body diagram, I've identified the positive direction to the right. So that one force is then equal to the mass of that one object, which is mass B, times the acceleration of that one object. Can I do anything with this? Well, I can. I in fact know mass of B and the acceleration of B, so I can go ahead and calculate that right away if I wanted. And that's one of the things I wanted to know, the magnitude of the force of mass A on mass B. Well, I want to know other things. What to do next? Well, I'm going to look at the second object and apply Newton's second law to it. So I'm going to isolate that object. What are the forces that are acting on mass A? Well, there's certainly the tension force, and it's acting to the right. I'm ignoring any vertical forces because the object is constrained to only move in the horizontal dimension. And I have a frictional force that mass B exerts on mass A. Now I identify right away that that is a Newton's third law force pair. The contact force of mass B on mass A is a Newton's third law force pair to the contact force of mass A on mass B. So I know that those two forces have to have equal magnitude and point in opposite direction. Since this force pointed to the right, that means this force has to point to the left. And those are the only forces then that are acting on mass A. So I can go ahead and sum them. The tension force has some magnitude T, I don't know what that is. It's pointing in the positive x direction. And I have this force of B on A. It has a magnitude, which is 20 newtons in fact. I've already calculated that. So I'll just indicate that with a F for simplicity. And it's pointing in the negative x direction. The sum of those two forces is equal to the mass of that object, mass A, times the acceleration of that object. That has a magnitude of the mass of A times the magnitude of the acceleration of A. And it's also pointing in the positive x direction. I can now turn this into a scalar expression using my notation for one-dimensional vectors. I have a magnitude of the vector where the sign indicates the direction of the vector. T minus F is equal to the mass of A times the acceleration of A. And do I have enough to solve? I do, because I know the mass, the acceleration, and I know F. So I can solve for T by bringing F on the right side of the equation, and I'm ready to plug in numbers. Now we have the tension, which is 220 newtons. Finally, I want to check. If I look at this expression, 220 minus the 20 newton force is 200, giving me a 5 meters per second squared acceleration to a 40 kilogram mass. Checking that in the end gives me some confidence that we calculated the right answer.